Now that we've seen all those fun visualizations, we should probably actually do a problem. In this case, let's consider a flow that is shocking where we want to figure out the Mach numbers upstream and downstream and the downstream temperature. We'll work with an ideal gas of specific heat ratio 5/3. The picture you should draw when you see upstream and downstream is this. So the idea is that we've drawn this so that the shock drawn there is stationary. We're in the reference frame of the shock. Upstream stuff is coming toward us, so it has not yet passed through the shock. Downstream stuff going away from us, it has already passed through the shock. They get the subscripts, X for upstream, Y for downstream. Don't ask me why, but it's what your book does, so I stuck with it. Now, we need more information to do anything interesting, but we don't know the Mach number, of course. But let's say that upstream we do know things like the temperature, pressure, the velocity, and the density. And, of course, we know that a shock forms. That's important. All right? Downstream, oddly enough, we don't know anything. So we don't know the downstream Mach number, we don't know the downstream temperature, and we're not given any other information. The interesting thing about shocks is you can work those out tacitly from using conservation of energy, momentum, mass, etc. Now, we won't have to do that explicitly. We'll just use the closed form solutions to those conservation laws that show up in your lecture notes. It's a lot easier not to derive those, believe me. Okay, so where do we start this? Well, where I would start is actually a discussion of the sound speed, because we want to figure out first the Mach number on the X side, since we have all that information on the upstream side. And your lecture notes present this result. I wanted to go through it quickly. The sound speed ultimately is equal to the square root of the partial derivative of pressure with respect to density at constant entropy. That's what that S subscript means. Well, we know actually what an isentropic process looks like for an ideal gas. Remember that P2 over P1 equals V1 over V2 raised to the K. K is the specific heat ratio again. So we could rewrite that in terms of density. Density is reciprocal of specific volume, so in that case, we just have that P2 over P1 equals the quantity, ρ2 over ρ1 to the K. Generally speaking, that must mean that pressure is proportional to density raised to the K power. So I'm going to write this as P equals A rho to the K, where A is some constant taking into account the fact that P and rho have different units, especially when rho has been raised to the K power. All right. So if we use that function, and remember this will be true for an ideal gas experiencing an isentropic process, constant S, then we can take its derivative, right? So let's take its partial derivative with respect to rho. We do that, and we get that it's AK times rho to the K minus 1. We don't have to worry about having weird powers of K. This will be true all the time. All right, so we'll move that result up. Next step, I'm actually going to rewrite rho to the K minus 1 as rho to the K over rho. That may seem like a weird maneuver until you remember, wait a second, the pressure itself was A times rho to the K. So that means we can substitute A rho to the K with just writing the pressure. So the partial derivative of P with respect to rho at constant S is K P over rho. Remember, C was the square root of all that stuff, so the sound speed is the square root of K P over rho. That's where the expression in your lecture notes comes from. Very useful for an ideal gas. Okay, so we're going to write that over there so that we remember it and can use it. We'll use it right now, actually, in constructing the Mach number upstream. So we want to know m sub x. Well, the Mach number is just the ratio of the flow velocity to the sound speed, so we can write that m sub x is just the velocity sub x divided by the sound speed sub x in the upstream flow. We'll put in the expression that we just came up with. C is the square root of Kp over rho, all with x subscripts. K doesn't change. It's the same fluid upstream and downstream. And now we'll just rearrange this a little bit so that our fraction isn't quite as messy. And we can put in these values. So 876 meters per second for velocity. Density was 0.87 kilograms per cubic meter. K is 5/3, unitless. And the pressure is 1 bar. Remember, you should work in pascals if you want SI units. So we'll put in 10 to the 5th pascals. Work all that out, and mx equals 2. So the Mach number was 2. It is definitely a supersonic flow, which we figured, it was forming a shock. All right, so we know mx, and we'll fill that in over in the table on the left. Remember, Mach number is unitless. It's the ratio of two speeds. Okay, next step. Well, we need to figure out the downstream Mach number and the downstream temperature. Let's start with the Mach number. So to calculate the downstream Mach number, we should appeal to one of these equations at the end of your lecture notes that relates Mach number on the downstream and upstream sides and the ratio of specific heats. You can derive these from conservation laws, but you kind of want to give yourself a whole afternoon to do so. That's why I don't go through it in the videos. All right, so the nice thing is we have mx, we just computed it, and of course we have k, it's 5/3, so we can just plug all that stuff into the right-hand side. So let's plug in numbers. All right, mx was 2, K was 5/3, and we need to simplify this a little bit. It's kind of a messy set of fractions. Simplify in one step, simplify once more. Now this is my squared on the left-hand side, so that equals 7/19, and we just need to take the square root of both sides to get that. The Mach number on the downstream side is 0.607. That makes sense. We have upstream conditions that generate a shock. The flow is moving supersonically. Downstream, it's moving subsonically. So the flow is moving slower than the speed of sound right there, so you wouldn't expect another shock to form or anything like that. Okay, so we'll fill in my equals 0.607 up there in our table. Okay, last thing we need to do. Let's figure out the downstream temperature. Again, you want to appeal to one of the equations near the end of your lecture notes that relates the temperatures, the Mach numbers, and the value of K. Now, it was nice that we went through and actually figured out the downstream and upstream Mach numbers first, because otherwise you couldn't have done this part, right? So we needed mx and my in order to calculate the temperature ratio. But now we have all the stuff on the right-hand side, so we can do that. Ty over Tx, if we enter in numbers, just becomes this. And we put in our new my value, 0.607, in the denominator there. All right, go through and simplify a little bit. And if we finally calculate all of this out, Ty over Tx becomes 2.08. So that's the temperature ratio. If we actually want to know the downstream temperature, well, fortunately we were given the upstream temperature, so we know that Ty in this case must be 2.08 times Tx. Tx was 400 Kelvin, so Ty is 832 Kelvin. This is characteristically what happens with shocks. Material upstream is cooler, passes through the shock, gets shock heated, and then downstream you can see that the temperature is considerably hotter. Here it's increased by over a factor of 2. I didn't want to do this in a video, but if we went through and calculated the entropy, you would see that actually the overall entropy has also increased downstream. Shocks heat fluids irreversibly. As you might expect, they're kind of violent structures.